This week we start our work with springs, and the key law for springs is Hooke's law. So on the left, this is what it should look like once you click on that link that I have in your Go Formative worksheets. That'll be on Google Classroom as well. And for now, we are going to start off with our intro for this. This one's a lot better than that conservation of energy one. Now, when you first get in here, reset all of this, it'll just look like this. We are going to go ahead and usually just have these boxes all clicked, this applied force. That way, no matter where I bring sort of our stretch, it'll show in the red what our applied force is. So right now it looks like I'm pulling this spring to the right, and then the corresponding spring force is to the left. Notice those are equal in magnitude, 75 newtons, 75 newtons, but opposite in direction. So our applied force is to the right, our spring force is going to the left then. Then this green arrow down here, that shows our displacement. So right now, when I exert a 75 Newton force on a spring, and I'll talk about this in a second with a spring constant of 200 newtons per meter, we have this displacement of 0.375 meters. Then just this sort of last box that we've clicked, besides just these values being shown, is our equilibrium position. So that way we can see visually on here where this starts if we just let the spring relax, or when we're not exerting any force. So when we let this relax, this little clamp doesn't need to grab onto it anymore because we're not exerting any force on this spring. This is its natural length, and that's called usually the equilibrium position. And so then this displacement is the distance that the spring is from that equilibrium. So if we have a displacement of 0.330 meters, we're 0.330 meters from that equilibrium line, from its natural stretch length. Okay, so a couple other things that we have in this simulation. We can drag this applied force down here. If you need to sort of fine-tune what that applied force is, you can use these, and that way you can sort of get it to exactly where you want it to be. The other thing that we have is this spring constant. A question that I'll ask you later is what happens as you sort of increase that spring constant. You can probably see that right there already. And then the overarching law here, called Hooke's law, that's going to be our sort of mathematical model that works pretty well to describe springs. And it's the equation for a spring force, and that's equal to negative kx. And k is our spring constant. So that's what you can adjust on the bottom left part of this simulation over here. That's what we're adjusting, is this k in our equation. And then we have x, and x is our displacement again. So again, that is the distance that we compress or that we stretch that spring from its equilibrium position. Now, what is this spring constant? Right. So that k in that equation is our spring constant, and basically that is our stiffness of a spring. So a really stiff spring, like the ones that they have, for example, in your car, would be like really, really stiff and would have a really high spring constant. Something like the one inside of a pen would have a much lower spring constant because it's a lot easier to compress those or to stretch those. Now the units for those spring constants you can already see in our simulation is newtons per meter. And basically that says that if we stretch, if our displacement is 1 meter for this spring, then we will have that many newtons of force required, or that many newtons of force that's exerted by that spring. So our units here, I'm just going to put it sort of above our newtons per meter for the spring constant. Our units for displacement are still generally in meters. So this way, when we multiply those two together, we will have our units work out, our meters are going to go away, and then we should just end up with the meters for our spring force. Now, a couple other things to notice as I pull this, like when I pull this spring, or if I push it in any direction with our applied force, you'll probably notice that we always have opposite directions, and I alluded to this before, opposite directions for our applied force. In this case, my applied force in red is to the left, so I'm pushing this spring, I'm compressing it to the left, and then we have a corresponding spring force, a reaction force, going to the right. And that's actually why this negative is in our equation for Hooke's law, because no matter what our displacement is, right, when our displacement right now is to the left, then our spring force is to the right. So our displacement and our spring force are always in opposite directions, and this negative is how we sort of figure that out. That's mathematically how that works out. Conversely, if I pulled this spring to the right, a positive sort of displacement, then our spring force right now is to the left, we would get a negative spring force. So that's why that negative is there. That should be just about all you need. The only other thing for this Monday work really is you trying to plug in some values. I give a couple sort of sample values, but that'll just be in the simulation. You can adjust the spring constant up here, you can adjust the applied forces, and then remember that it'll give you your displacement down here with this little green arrow. Do remember to check all of these boxes so that you can actually see all of the things that you need to see to analyze these springs how we're going to today. Good luck.